Electromagnetic interference, or EMI, is a crucial concept in modern electrical engineering. At its core, EMI refers to any unwanted electromagnetic energy that disrupts the normal operation of electrical circuits. This interference can come from both inside and outside a system, and it often leads to degraded performance or even system failure. Engineers working on power distribution, industrial controls, or automotive electronics, understanding EMI is essential. It's not just about fixing problems after they occur. Recognizing EMI early in the design phase allows for proactive solutions like grounding and shielding. EMI is different from intentional electromagnetic signals, such as those used in radio communications. Instead, it's an unintentional byproduct of everyday electrical activity. By grasping the basics of EMI, engineers can build more reliable and robust systems that stand up to real-world challenges. EMI can originate from a wide range of sources, both natural and man-made. Natural sources include phenomena like lightning strikes, solar flares, and geomagnetic storms. These events can inject powerful electromagnetic pulses into power lines and communication cables, sometimes overwhelming protective devices. However, in most engineered environments, man-made sources are the main concern. Everyday devices such as switching power supplies, electric motors, RF transmitters, and even fluorescent lights can generate EMI. For example, variable frequency drives in industrial motor control systems produce harmonics that travel through shared power buses, turning ordinary equipment into unexpected EMI emitters. Even digital clocks and microwave ovens can create interference during their on-off cycle. Understanding where EMI comes from helps engineers map out potential interference paths and design systems that are more resilient to these disturbances. EMI is generally classified into two main types: conducted and radiated. Conducted EMI travels along physical conductors like power lines or cables, directly transferring unwanted energy from the source to other parts of the system. This can happen in two modes: differential mode, where noise flows in opposite directions across signal pairs, and common mode, where currents move together relative to ground. On the other hand, radiated EMI moves through the air as electromagnetic waves, turning wires and components into unintended antennas. Radiated EMI is especially problematic at higher frequencies, where it can easily jump between systems without any direct connection. For example, unshielded motors can radiate magnetic fields that interfere with nearby electronics, while high-frequency transmitters can couple energy across gaps in enclosures. Knowing the difference between these types is key for selecting the right testing and mitigation strategies. Effects of EMI on electrical systems can range from subtle to severe. At the most basic level, EMI can degrade signal quality, causing data errors or inaccurate sensor readings. This is especially critical in applications like renewable energy inverters or precision industrial controls, where even minor noise can have big consequences. More serious impacts include unexpected shutdowns or malfunctions, such as false trips in protective relays or destabilized control loops. Safety-critical fields like aerospace or medical devices, EMI can pose real risks. Imagine a navigation glitch in an aircraft or a pacemaker malfunction. Beyond safety, EMI can also have economic consequences. Failing to meet regulatory standards can lead to costly redesigns, delayed product launches, and even legal liabilities. That's why comprehensive EMI testing and robust design practices are essential for any modern electrical system. Understanding the sources, types, and impacts of EMI empowers engineers to design systems that are both reliable and compliant with industry standards. By treating EMI as a system-level challenge, rather than an isolated issue, professionals can implement effective strategies like filtering, grounding, and shielding right from the start. As technology continues to advance, with trends like 5G and electric vehicles on the rise, staying informed about EMI fundamentals is more important than ever. Ongoing education and proactive design are the keys to innovation without disruption, ensuring that our increasingly connected world remains safe and efficient.